So yeah, I'm Jesse Adams. I'm going to talk about Flatcam, our ultra-compact lensless imaging system. And so before we get started, we just want to introduce our team from Rice University. We have over 80 years of combined experience in computational imaging, machine learning, optics, and nanophotonics. And so we looked at the last 20 years or so and looked at the shrinking of size and reduction of cost of imaging systems. And we looked at the innovations like high-resolution camera phones, handheld light field cameras, and endoscopes that fit on a pill that you can swallow. And we wondered what applications are possible if we continue to shrink the size and cost of these imaging systems down to something near the size of the imaging sensor itself, and how might we achieve this? So we looked at imaging systems, and we know that cameras, imaging systems, are dominated in size by the focal length of the lens. And this is true for cell phone cameras as it is for complex microscopes. And if we remove that lens, we destroy most of the information from the scene. But what we do with Flatcam is we replace that lens with a very thin, specially designed mask that allows us to reconstruct an image that's very close to that scene. More specifically, we record an encoded image that you see as Y. That pretty much looks like nothing recognizable. We use that image as well as our specialized design mask and model. We solve an optimization problem, and we're able to output an image that looks like that on the right-hand side. And let's look a little closer at the results. So we can see the cell phone image is nice and sharp, and we see the Flatcam is maybe a little less quality. But so why would we want to use Flatcam? Who cares? Well, our technology allows us to make a device that's less than 500 microns thick, that's less than 5 human hairs, that's less than 0.2 grams in weight, and can be integrated into the semiconductor fabrication process, making the cost just barely that over the imaging sensor itself. And so we can look at a video where it may be a little bit low quality here, but we're able to do inference tasks like face detection and face verification. And so we anticipate having applications in things like IoT, where we want new user experiences or are able to collect data on something that's extremely cheap, but also very small and thin. And also something that's extremely lightweight for surveillance or rescue, like the micro drones that you see here. And in addition to doing photographic images, we can also reconstruct high-resolution, three-dimensional microscopic images. So we can take a large, expensive microscope that you see here, reduce it down to something that you can put on the tip of your finger, and we can do biological imaging, like this microorganism that's expressing a fluorescent protein. And so with that, we expect to have applications in endoscopy, lab on chip, and wearables for high resolution, where size is a premium, and that's what everybody's looking for. So in summary, we're looking for impact where cost, weight, and size are a premium, things like IoT and surveillance, as well as things in biomedical application where we want to do something that's cheaper, less invasive for maybe point of care, or wearables where you want to get more than just a bare sensor information, get something that's high resolution. And with that, I'd like to thank you, and I welcome any questions.
Fantastic, well done. Let me move some mics up here. Does anybody, you have one mic? Fantastic, there's 2 mics, great. Okay, hands up, go.
Hi, very exciting technology. I've heard about this for a couple of years. So I'm just curious, what has been the main challenge? Is that in terms of scaling it up? Have you run into any difficulties in kind of making this mass?
So we're developing some new masks that I can't go into yet, but yeah, part of it will be scaling. So on the first designs were amplitude masks with simple photolithography, and it's an easy system to scale. So it depends on the quality of the image that we're looking for right now. So as we move forward, I'll find out very quickly in the next actually 3 to 6 months how hard that'll be to scale up.
Who's next? Erik. Can you get all the mics on? What number you have on that? 7. Can you switch mics? Or Matt can go then.
Should I go? Could you give me a quick idea of the computational complexity involved in reconstructing the image? If I look at like a company like Pelican, I feel like a lot of what happened there was they just couldn't get that stuff to run in real time with a reasonable silicon cost.
Sure. Yeah, so some of our models basically just a matrix multiplication. So we actually anticipate that you'll be able to do computation on chip, especially with new sensors that have multi-layers that can do some of that computation. So it's actually fairly simple. We're also looking at convolutional models as well, which are very fast and pretty optimized with today's systems.
And Erik?
Okay, very cool. Do you have any interesting examples of what you can do when you have many of these sensors?
Not yet. We've always posed that we can do arraying of the sensors, and of course, our field of view is the size of the sensor itself. So if we had very large sensors, we can just put very large masks or mini masks over it. But we don't have any examples yet. But it's something we're very interested in.
Yeah, I'm thinking stereo, multi-view geometry.
Yeah, absolutely.
Okay, yeah.
Jason?
So I saw two things that are competitive advantages. One is size, and one is cost. What is it that's the pull? Because there's some great stuff in microscopy, coming out of UCLA and making these things really, really small. What is it that you're being pulled to go do?
So the pull in, especially in biomedical, is doing something that maybe can fit inside a vein as opposed to just something that you can put in some canal that's a little bit larger. And so not only doing that, but having a sensor that has the full field of view of the entire object that you're using in a biomedical application, for example. So it would be something where you put it in and take it out, and that's it. You get all your imaging. You don't have to have a surgeon that puts an endoscope in, turns it, looks around, and has a difficult mechanical structure to it. So that's kind of what we're looking at. Does that make sense?
One last question, anybody? We're all set, judges?
Is there any competitive landscape there?
What's that?
Are there any competitors, or are you the only ones?
Yeah, I don't think there's some other schools that do some different. There's nobody commercially right now that's doing it. There's some people that we've talked about collaborating, doing some review papers on with, but nobody's making a real push to make super flat stuff, and that's really where we find our niche.
Fantastic. Round of applause for Jesse. Thank you very much, Jesse.